All right, so the next one we're going to take a look at, this one's an interesting one. I think it's missing some information that is absolutely vital in here, so I'm going to give you some of that information. It should remain the same number on everyone's, and I'm also going to put a post on Edmodo so that we can actually do it. Thought about pulling the question, but I really like the question, so we're going to run with it. The wind blows with a speed of 29.1 meters per second over the roof of your house. Assuming the air inside the house is relatively stagnant, in other words, not moving, what is the pressure difference at the roof between the inside air and the outside air? So what we're going to do, we're going to draw this laughably oversimplified. Here's the ground, here is your house, and here's the roof. Now what they're saying is, we have a relatively thin roof, and we've got the wind blowing, using the same stuff that we did in class. It's blowing like this, and it is blowing with a velocity of, let's see, 29.1 meters per second. And inside your house, because we're not opening the windows or anything like that, you've got a bunch of air that's just kind of chilling there. It's relaxing, not moving a whole lot. This is the air on the inside. It has a velocity of 0 meters per second, or pretty close to that. Maybe you want to run a fan or something, but anyway, 0 meters per second will be a good approximation on this. It's not moving very fast one way or the other. All right. Now, 29 meters per second is, if you remember back to when we did kinematics, to put this in perspective, that's really fast. That's actually a little bit greater than 60 miles per hour. So we're dealing with some not pleasant weather in this particular problem, at least with the numbers that I have here. All right. But we want to know what the pressure difference is between here, this part of the roof, and here, this part of the roof. Now for this, we're going to use Bernoulli's equation. So we've got a pressure on the outside, and we've got a pressure on the inside. Now, the inside pressure is going to push up on the roof. The outside pressure is going to push down on the roof. Now, this is the way that we showed it when we introduced the idea of dynamic pressure, but we're actually going to use all of Bernoulli's equation to actually solve this, which is when we started using the numerical approaches. All right, well, Bernoulli's equation says that we've got some relationship between these flows, so I'm going to have the pressure in the blue area plus, so Bernoulli's is the fluid pressure plus the dynamic pressure plus the hydrostatic pressure, and we say that that is equal to a constant for related flow fields. This one's a little iffy because we don't have all of this being part of the same fluid, but most likely your house is not completely sealed, so it'll be a good enough approximation that will get us the information that we're looking for. This will be equal to the same values in the green area. I'm going to squish them in here, but we're going to have the dynamic pressure 1/2 rho V in the green area squared plus our hydrostatic pressure, which is rho GH. Now, depending on how I'm doing this, sometimes I put these in different order. I usually put the fluid pressure here, but sometimes I'll switch the hydrostatic and the dynamic pressure. When we're adding stuff, it doesn't matter if this is 1 plus 2 plus 3. We could also make it 1 plus 3 plus 2. We can switch these, and it doesn't matter. Addition, the order does not matter. So, you may have seen it in class where I switch these two. I may go back and forth on that. I apologize. But Bernoulli's basically says we take all of these together, and they'll be equal to a constant. Now, as a reminder, this is actually a statement of conservation of energy. You can see that because this looks like 1/2 mv squared kinetic energy, and this looks like mgh, which is gravitational potential energy. We've got a little bit more because this is much more complicated with fluids, but Bernoulli's equation is applying conservation of energy onto fluids. All right, now that all that's out of the way, let's go through and take a look at this. First off, we might have a difference in hydrostatic pressure, but if we're looking right here for the inside of the house and right here for the outside of the house, they're both pretty much at the same height. The difference in height is going to be a really small number, so we could put it in there, but we're not really given information on that. That's why I said we're going to laughably oversimplify this and ignore the thickness of the roof. Even if it is a moderately thick roof, it's not going to make a huge difference when we look at the density of air, the hydrostatic pressure of air. Here's the thing that is actually missing. The density of air for this problem is about 1.29 kilogram per cubic meter. I should also have that posted so that you all can gain access to that, but this is one of the numbers that we're actually going to need on this, mainly because we have the density show up here and we're going to solve for that. Now, we're going to say that whatever h is, it's the same for both sides, and so these are actually going to be the exact same number. Not 0, but they'll be the same number. If this is 10, this side is 10, and I'd subtract 10 over. In short, they're both going to have the same hydrostatic pressure because they're both at about the same height, h. So I'm actually going to ignore that for this problem. Now, if I had one of them where it was way down here and one of them way up here, there'd be a noticeable difference in the height, and I'd have to put those values in. But if I put in a height of 3 meters, for instance, I'm going to get a number here, and I'm going to get the same number over here, and I subtract it from one side, and it'll disappear from the other side. In short, what we end up with is the following. The pressure plus 1/2 rho v squared in the blue section is going to need to be equal to the same thing, the pressure plus 1/2 rho v squared in the green section. Let's fill in a few things. We know that v in the green section is equal to 0, so when I plug 0 in here, this whole term disappears, and I end up with the following. P, the blue, plus 1/2 rho v squared for the blue equals the pressure inside the house, the green area. They want us to find the difference in pressure, which is one pressure minus the other, so I'm going to subtract off P from both sides. In this case, it's P in the blue area. I get the following. 1/2 rho v squared, which is the dynamic pressure, will be equal to the pressure on the inside of the house minus the fluid pressure on the outside of the house. This is actually what we're looking for. This is the difference in pressure. So if I take the high pressure, because it's not moving here, I have high pressure here, and low pressure here, we're looking for the net pressure that we've got on the roof here. In other words, the difference in pressure, the big one minus the small one in this case, is how it conveniently comes out. And I find, well, this is what I'm looking for, so I have 1/2 rho, this is where we need the 1.29 kilogram per cubic meter, which is the density of air. Technically, this is the density of air at about probably 40 degrees Fahrenheit. The temperature will actually cause the density to change ever so slightly. And then v squared, we said that the velocity was 29.1 meters per second, quantity squared, and that is going to be equal to, we could call this delta P. It's our difference in pressure. Delta is usually final minus initial, but we're going to see that we can also apply it in times when it's a difference between one location and another. Wouldn't necessarily call it a change, but you can if you'd like. Go through and I solve this. We're pretty much done. 29.1 squared times 1.29 times 1/2. I come up with the following. That the pressure difference between the inside of the house and the outside of the house comes up to 546. Well, these are pressures. I have kilogram per cubic meter. This is one where it gets a little weird, but we have meters squared per second squared. Go through and double check the units, but you will find that since we're finding a pressure, it will come up to pascals. This is the pressure difference. Now that by itself is not necessarily useful. What we'd like to know is, what effect is that going to have on the roof? And so the next question is, what net force does this pressure difference produce on the roof, having an area of 104 square meters? So what they're saying is, your roof has an area, and the area is equal to 104 square meters. Okay, well, if this is the net pressure, I have some pressure on bottom and some pressure on top, but if they were the same, they'd cancel each other out and we wouldn't have any effect. What we're saying is we have 540 some odd pascals more pressure on bottom so we can find the net force pushing up. This is one thing that we didn't do with the ping pong ball in class because I didn't really have the numbers for it, but here's a place where we can find them. In this case, we know that pressure equals force divided by area. There's that equation again. We know that the pressure difference, the pressure that we're looking at, is 546 pascals, and that'll be equal to the force on the roof divided by the area, 104 square meters. I can now solve this out, and I can find that the force on the roof, multiplying both sides, is a very noticeable 56,804, but I'm just going to call it 800 newtons. Put SI in, get SI out. 56,800 newtons. Now this, let me double check our values here. Yep, looks good. And so that we can put this in perspective, remember, 1 pound of force is equal to about 4.4 newtons. So if I divide this by 4.4 newtons, I end up with the following. This force that's on the roof is actually about 13,000 pounds. Comes up to about 6.5 tons. That's a lot of force. That's also why in very large windstorms or anything like that, you have weird things that can happen to houses. In fact, the roof is usually pretty well designed for this, but I want you to think about this. What if instead we had a window that was right here? We had wind blowing past it. So we have low pressure air on the outside of the window and high pressure air on the inside of the window. What would end up happening? Well, if the force gets high enough, if the pressures, I should say, get to a noticeable difference, and then that results in a large enough force, the window will actually break. But here's the important part. Outside we have low pressure, because that's where the wind is. Inside we have high pressure, so when they break outward. You may have heard before, especially in the area that we are in, that in a tornado, when you have very high-speed winds, that the windows have a tendency to break, and you may have heard that they have a tendency to break outward. That's why. All right.